Welcome back to problem 5 of exam 2. Here we have another conceptual question that states, suppose the Earth had no atmosphere and a ball was fired from the top of Mount Everest in a direction tangent to the ground. If the initial speed were high enough to cause the ball to travel in a circular trajectory around Earth, the ball's acceleration would blink. And we're given a couple options here. Now, analyzing this, first off, there's no atmosphere, which means there's no air resistance. So the only two accelerations that are enacting on the ball are the centrifugal acceleration and the gravitational acceleration. And because this is constantly going in an equal circular motion, it's in equilibrium. So we can say that the gravity accelerational is equal to the centrifugal acceleration. And we have equations for both of these, right? So we have, for the gravity, we have the gravitational constant times the mass of Earth, and all of that over the radius squared. And according to this up here, that is equal to velocity squared over the radius. Now, to prove that these are equal to each other, let's go ahead and analyze what values we have. So we know that the gravitational constant for Earth is equal to 6.674 times 10 to the negative 11th power. Okay, and we know the mass of Earth is approximately 5.972. So that's supposed to be a 2, not a 9. Give me 1 second here. All right, 2 times 10 to the 24th power. And then we have the average radius of the Earth, because it does fluctuate. So we'll say the average radius of the Earth is equal to 6.371 times 10 to the 6th power. Okay. And then we know the height of Mount Everest to be 8.848 times 10 to the 3rd power. Okay, and so in these equations, our radius is going to be the radius of Earth plus the height of Mount Everest. So let's go ahead and calculate what our r is real quick, our radius. So we have 6.371 times 10 to the 6th power plus 8.848 times 10 to the 3rd power. Okay, and that's going to give us 6379848. Okay, that will be our radius. So let's go ahead and manipulate this equation here so we can isolate for velocity, because that's the one variable we don't know. So we'll go ahead and multiply both sides by radius. So this cancels out. There'll be 1 radius left. And then we'll square root both sides, isolating for the velocity. So we have the gravitational constant times Earth's mass times the radius, square root, and that is equal to the velocity we need to reach the equilibrium state. So let's go ahead and input the values that we have here. So put that in a root. We have the gravitational constant, 6.6, and actually we'll put these in parentheses to better understand them. 6.674 times 10 to the negative 11th power, and that will be times Earth's mass, which is, let's see, 5.9 972 times 10 to the 24th power. Okay, and all of that will be over r, which is 6379848. Okay, and that will be equal to our velocity. So our velocity is 7904.02. We'll do a little bit of rounding because we only need to be approximately close to g. If this is our answer, we don't need to be exactly gravity. Okay, so now we have velocity and we have all the other variables. We just need to prove this is equal to gravity. So let's go ahead and input that in. So we have 7904.02. That's going to be squared all over our radius there, 6379848. And this is equal to our centrifugal acceleration. So let's go ahead and input that into our calculator. 7904.02 squared. And that will be all over 6379848. And that right there, 9.79 is equal to our centrifugal acceleration, which is approximately equal to our force of gravity, which is equal to 9.8. And that is our proof for why answer B is the correct answer for problem number 5. Thanks for watching.